Our second programme on mathematical modelling is about drugs and the way they act to relieve illness. We shall find that the mathematics involves time as one of the variables. These time-dependent models are set up by using an input-output principle, and the resulting mathematics is that of differential equations. Well, the drug we're going to talk about is called theophylline, and it's used in the treatment of asthma. To find out about that treatment, we went to Oxford to see Dr. Geoffrey Aronson.
Asthma is a disease which affects the lungs, and in particular the airways in the lungs. Patients with asthma have constriction of the airways, and they have difficulty in breathing, particularly in breathing out. Now, there are many thousands of people in this country who suffer from asthma, but of those, only a handful are admitted to hospital during the year for emergency treatment. And when they are admitted for emergency treatment, we use a drug called theophylline. Theophylline is present naturally, for example, in tea leaves, and we give it intravenously in an acute case. Now, until the last few years, there was no good way of knowing how much drug any individual patient needed to achieve a good effect. A typical dose might be 250 or 500 milligrams of aminophylline intravenously. However, more recently, some research has led to our being able to predict with a greater degree of confidence exactly what dose an individual patient will need. Obviously, we want to give the dose which will produce the best effect in an individual patient, and it turns out that the effect of the drug is related to the concentration of the drug in the plasma. By concentration, I mean the amount of drug present in a unit volume of plasma. Now, we know that the effect is related to the concentration of drug in the plasma because experiments have been performed relating the two. And the way we measure the effect is by measuring how well the patient is able to breathe. And to do that, we can use a variety of different techniques. But for bedside practice, for looking at the patient, we use a simple machine like this. It's called a peak flow meter. And it measures how fast the patient can blow at an instant. He puts his mouth around the mouthpiece, takes a deep breath in, and blows as hard and as fast as he can into the machine. The machine then registers a figure, which we call the peak flow rate. I'll show you. My peak flow rate is 640 litres per minute. If we then relate the peak flow rate in an individual patient to the plasma concentration of theophylline, we find that there is a relationship between the peak flow rate in litres per minute, that's the ability of the patient to breathe properly, and the concentration of theophylline in his plasma, which we've measured in milligrams per litre. In fact, it's a linear relationship between plasma concentrations of about 5 milligrams per litre and about 20 milligrams per litre. The peak flow rate increases linearly with increases in plasma theophylline concentration. If the plasma theophylline concentration is less than 5, there's very little effect. And at values greater than 20 milligrams per litre, there's very little additional beneficial effect. Plus the fact that at that time the patient is likely to become toxic from the effects of the drug. By that I mean he may feel nauseated, or he may even vomit. In severe cases, he may have a convulsion. Obviously, we don't want to make the patient toxic. So we can now define ranges of concentrations in which we're interested. At plasma concentrations of less than 5 milligrams per litre, there is little effect. At plasma concentrations above 20 milligrams per litre, there is a toxic effect. And at plasma concentrations between 20 and 5 milligrams per litre, there is a beneficial effect, or as we call it, a therapeutic effect. Thus, the physician has to be careful in choosing the correct dose for his patient if he wants to produce a therapeutic effect, while at the same time avoid causing toxicity.
So that's the problem. To administer this drug so as to achieve a concentration somewhere between 5 milligrams per litre and 20 milligrams per litre, somewhere in this therapeutic range. I'm going to assume that the doctor is in fact going to aim for the centre of this therapeutic range for a concentration of 12 milligrams per litre. Now, of course, if you want to produce that concentration, then all you have to do is to make up a suitable dose according to the amount of blood plasma that the patient's got. Because there's a simple relationship between concentration and quantity and volume. If you put in a quantity Q, milligrams, and that is spread over V litres and produces a concentration of C milligrams per litre, then the relationship between C and Q is given by C equals Q over V, where V is the volume into which you're putting this drug. What is V? Well, it's certainly not the volume of the patient's body. In fact, it's really a sort of nominal volume, which can only be properly defined for a patient by turning that relationship inside out. If we put in a known dose and measure the concentration, then from these two values we should be able to find V. But even that very simple idea is fraught with difficulties, as Dr. Aronson tells us.
The way I'd determine the apparent volume of distribution in an individual patient would be to inject a known quantity of drug into that patient's bloodstream, and then to measure the plasma concentrations at certain times after having given the drug. I would inject the drug into a vein in the patient's arm, inject it slowly, and then wait maybe 5 or 10 minutes to allow the drug to equilibrate throughout the blood and to start distributing into the tissues. And then I'd take blood samples from the other arm to avoid possible contamination from the injection site, typically at intervals, say, of half an hour. I'd take the blood back to the laboratory, analyze the plasma for its theophylline content, and then, when I studied the results, I'd find out that the plasma theophylline concentration varied with time, something like this. It starts quite high, but then falls very rapidly over the next few hours. Now, I can't tell the apparent volume of distribution from these data. At times when I know the concentration of theophylline in the plasma, I don't know how much drug is in the body, because the drug is distributed rapidly through the tissues, and some of it goes to the kidneys, which excrete it into the urine. However, at a time when I know how much drug was in the body, that is, the dose which I gave at the beginning, I don't know what the plasma concentration was. So I have to try and analyze these data mathematically. I have to try and derive a function which will tell me the relationship between plasma concentration and time. And to do that, I need to develop some sort of mathematical model. If I can develop a satisfactory mathematical model, then I can do two things with these data. Firstly, I'll know how to extrapolate this line back to the vertical axis, which will allow me to work out the apparent volume of distribution. And secondly, I'll be able to extend it in this direction, so that I can tell at what time the plasma concentration falls below our theoretical minimum therapeutic value, and I'll know when I ought to give the patient another dose of theophylline.
So you see, the whole thing is getting a little bit more complicated than we thought. And this very simple model won't do. In that picture, we thought of the patient as just a vessel with a known volume into which we put a quantity of drug in order to produce a required concentration. And now we discover, first of all, that there are problems associated with what the volume is exactly, and secondly, that the vessel leaks, as it were. As soon as the drug's put in, it starts being excreted. What we have to do is to recognize that quantity and correspondingly concentration are both really functions of time, that they change from minute to minute. And so we shall have to recognize that Q is a function of time and that correspondingly C is a function of time. But of course, at any given time, there will still be this basic relationship that the concentration is the quantity divided by the volume. What we need to do, though, is to set up some mathematical model which will explain the experimental results that Dr. Aronson has found. We need to set up a model in which we recognize the dependence of both concentration and quantity on time.
The input-output principle is a pretty general method for setting up differential equations as mathematical models for time-dependent problems. Now, the problem we've got here is to find out how the quantity of theophylline in a patient's body will change with time. And the principle tells us that the accumulation of any substance over a period of time is equal to the input during that period minus the output during that same period. Let's look at a numerical example. Here's a patient with 100 milligrams of theophylline in his body, and suppose he gets a dose of 250 milligrams. That would bring the quantity up to 350. But suppose that during the same time interval he excretes 200 milligrams. So that will bring it down again to 150. So the net accumulation is just 50 milligrams, and that is equal to the input minus the output. Now we want to change this principle from words into symbols to be able to use mathematics on it. And to start with, we'll need symbols for the beginning and the end of the time interval. Let's take the beginning to be t, and so the quantity at that time will be q of t. And let's take the end to be a little bit later, so that the end of the time interval will be at time t plus delta t. And the quantity at that time will be q of t plus delta t. Then the difference between those two quantities at the beginning and the end will be the accumulation during that time interval of length delta t. Now, to complete our equation, we need to know something about the input and the output. I'm going to take the simplest case here. I'm going to assume that the input is 0. That corresponds to the situation when the patient is not actually receiving any injection of the drug. As far as the output goes, we have to make some kind of a physiological assumption here. The simplest assumption, and the one which has been found to work, is that we assume that the output is proportional to the quantity of the drug in the patient's body. Let's write it out in symbols. This is what it'll look like. Now, I've also assumed that the output is proportional to delta t, because the longer the time interval, the more output will be. And finally, our constant of proportionality, lambda. So that's the mathematical model. And in setting it up, I've used, first of all, the input-output principle to get the left-hand side, and on the right-hand side, an assumption about proportionality. Now, there's one more step in setting this equation up, because some of the approximations we've made are the better, the smaller the time interval delta t. So it will be a good idea to turn this equation into a differential equation by taking the limit delta t goes to 0. To see how to do that, let's look at the left-hand side first. It's like part of the definition of a derivative. To make it more like a derivative, let's divide both sides of the equation by delta t. Then the right-hand side will simplify like this. Now, to complete the process, we'll take the limit as delta t goes to 0. The right-hand side is unaffected because there's no delta t in it now. And the left-hand side just becomes the derivative of q. So there's our differential equation, and it's a mathematical formulation of the time-dependent problem. Remember that in setting it up, I assumed first that there's no input, and secondly, that the output in a short time interval is proportional to the quantity present. Now, when we've solved these equations, then the next stage of modeling will tell us whether that proportionality assumption is justified when we compare the predictions of this equation with reality.
So, the suggestion now is that this differential equation governs the way in which the amount of theophylline in the body varies with time. Of course, you get an initial input from the doctor. In fact, at t equals 0, the quantity in the body is d, the dose. And this is our mathematical model. And this is what we want to solve. Now, that differential equation appears in the text in a slightly disguised form. There, Q was the quantity of uranium, and the rate at which the uranium decreased was proportional to the quantity there at any time. And the solution of that differential equation is the same exponential law of decay. If, in fact, this solution is to satisfy this condition, then it simply means that the constant A, which remember could be anything, has got to be equal to D, the initial dose. So here's the solution of our mathematical problem, and it really ought to go in the mathematical solution box. But of course, what we're really interested in is the concentration. And I can get the concentration simply by dividing that thing through by V. And I get the concentration at any time is d over V, which is the initial concentration, multiplied by e to the minus lambda t. So there's the solution of our mathematical problem, and now we must compare it with reality. Well, the first step in comparing it with reality will be to look graphically at the way in which C varies with T. If we start with a concentration of 10 milligrams per litre, then as time passes, the concentration falls like this. It's exponential decay. If the concentration starts at 20 milligrams per litre, though, then this is what happens. And for any initial concentration between 20 milligrams per litre and 5 milligrams per litre, we get a variety of curves like this. Of course, the graph also depends on the constant lambda. If lambda is large, then the concentration falls rapidly. If lambda is small, it falls more slowly. So, those are the qualitative predictions of our model. But does any one of those curves actually fit Dr. Aronson's experimental results? Well, it's very difficult to know whether, in fact, a curve fits a set of points. But we can make the job a lot simpler if we use a technique that you've met already. You called it straightening curves. If we look back at the solution of our differential equation, then if we take logs of both sides of that equation, we get, on the left-hand side, the log of C of t, and on the right-hand side, we get the log of d over v, and then, because I'm using logs to base e, the log of e to the minus lambda t comes out very simply as minus lambda t. Now, that relationship is very much simpler if we think of the log of C of t as one of the variables and t as the other variable. In fact, we've got this thing here, which, although it looks complicated, is just a constant, and another constant there, and that's the equation of a straight line. So, if our model is correct, and in particular if the assumption behind it is correct, then we should find that when we take Dr. Aronson's experimental results and plot log of concentration against time, then we get points which lie on a straight line. Well, this is what we actually got. And you see, the points do in fact line up. And the fact that they lie on a straight line validates the model. So we've now validated our mathematical model. But in fact, we get more out of it than that. For instance, by looking where the best fit line cuts here, we can find the value of this lot here, log to base e, of d over v. And in Dr. Aronson's experiment, he was giving a known dose, so we can use that to find v. And then, if we take the slope of this line, then the slope of this line will simply be the other constant in here, lambda. Now, so far, we've talked about just doing one experiment. But of course, Dr. Aronson and his colleagues can repeat these experiments with different patients. And when they do that, they find two things. they find, first of all, that lambda doesn't vary very much from patient to patient. And the second thing they find is that V, the apparent volume of distribution, depends in a very simple way on the weight of the patient. For each kilogram weight of the person, the volume of distribution is half a litre. So there's a very simple rule of thumb. And remember, we're talking about doctors faced with patients having acute asthma symptoms. And they don't have time to do experiments on them. So the doctor has a very simple rule of thumb. He simply takes the weight of the patient, finds his apparent volume of distribution, and calculates an appropriate dose. That gives him a concentration in the blood plasma of 12 milligrams per litre, and how that 12 decreases then appears in the rest of our mathematical model. It in fact decreases like this. And you notice that after a comparatively short time, you're beginning to move out of the therapeutic range. In fact, after about 4 hours, a concentration of 12 is reduced to 6. About half the drug is gone. In the terminology of radioactive decay, this is the half-life of the drug. That's about the time, then, that the doctor will be thinking of giving the patient another injection so that he doesn't fall below the therapeutic range. And then he'll have to have another injection, and another injection, and another injection, and so on. So, our mathematical model predicts that this is the way in which the concentration of theophylline will vary with time if we give repeated injections. And with the aid of our mathematical model, we've been able to discover not only the dose which will put the patient into the middle of the therapeutic range, but now also the interval between injections. But perhaps the last word should be with Dr. Aronson.
Now, although that's a perfectly feasible way of treating asthma with theophylline, it does mean a lot of injections for the patient, perhaps 1 every 4 hours or less. And we can improve on that. We don't have to give the patient repeated injections. We can give him a slow intravenous infusion. When we give the drug by intravenous injection, it immediately starts to leave the body. And we can replenish the amount of drug that's leaving the body by giving a little at a slow rate. And an intravenous infusion achieves this. It's done by slowly feeding drug in solution into a vein in the patient's arm.
Well, that idea is clearly going to change our mathematical model. We're going to have to incorporate into the differential equation a term representing input from that infusion. But the mathematics is not very difficult, and so we're letting you look at the implications of that new model.